Okay. So now the chapter is cyclic groups, and in this chapter we are going to talk about their properties, how they are forming, and how we can use them to understand groups more, other groups more. Okay. Now, few theorems, quotes actually. The notion of a group, viewed only 30 years ago, is the epitome of sophistication, is today one of the mathematical concepts most widely used in physics, chemistry, biochemistry, and mathematics itself. This said by Alexei Sosinsky in 1991. Other one is, indeed, group theory achieved precisely that a, uni- a unity and indivisibility of the patrons underlying a wide range of seemingly unrelated disciplines. Yeah, and this is said by Mary Olivio in the book The Equation That Could Not Be Solved. Now we will talk about the properties of cyclic groups. So if we recall from the chapter 3 that a group is cyclic if there is an element A in G such that it can generate the whole group. So if we say that a group is cyclic, G is cyclic if there is an element A in G such that G can be written as its powers, given that n is coming from the integers. Now, such an element is called A is called the generator of G. Such an element A is called a generator of G. In view of the notation mentioned in the preceding chapter, we may include that G is cyclic group generated by A, and we can write the notation which we used in chapter 3, that we can write that G is equal to S, where A is the generator of G. Now, in this chapter, we examine cyclic groups in detail and determine their important characteristics. Now, let's start with an example. So, example 1 says that the set of integers under addition is cyclic. The set of integers z under addition is cyclic. Both 1 and -1 are generators. Both 1 and -1 are generators. recall that 1 power n is interpreted is 1 power n is interpreted is 1 is added n times. When n is positive, when n is positive and is -1 plus -1 can also be written as mod of n times n terms actually. When n is negative, okay? Right. Similarly, the other cyclic group is the set Zn, which can be written as 0, 1, dash dash, and -1 for n is greater than or equal to 1 is a cyclic group under addition modulo n. We use the short notation mod n. Again, 1 and -1 are generators. Again, 1 and -1, which is this time equal to n -1, are generators of the group. Now, unlike Z, which has only 2 generators, Zn have many generators, depending on which n we are giving. So let's say we have another example, which is, it says that consider Z8, which is generated by 1, generated by 3, generated by 5, and also generated by 7. To verify this, for instance, that Z8 is generated by 3, we say that, we note that the set, the 3 generates these elements like 3, 3 plus 3, 3 plus 3 plus 3, and so on, which is going to be the set 3, 6, now 9. Under mod 8, it is going to be 1. Then 12. Under mod 8, it is going to be 4. And 16. Under mod 8, it is going to be 0. 12, which, no, after 12, it is 5. 15, which is going to be 7. Under mod 15, then 18, which is going to be 2. Then 21, which is going to be 5. And then 24, which is going to be 0, which is itself Z8. Thus 3 is the generator of Z8. On the other hand, 2 is not a generator. 2 is not a generator since 2 only generates following, which is 0, 2, 4, 6, which is not equal to 0. Now, if you see, let's take another example. And this says, if you see the example 11 in chapter 2, which we have given over there in chapter 2, the state we have considered there was U10, which is actually equals to 1379. Now, this can be written as 3 power 0, 3 power 1, 3 power 3, and 3 square. So that means U10 have generator 3. 3 generates U10. Also, 1, the 1379 can also be written as 7 power 0, 7 power 1, or if you write 3 first, then 7 power 3, 7 power 1, and 7 square. So it is generated by 7. So both 3 and 7 are generators for U10. Okay. Now, quite often in mathematics, a non-example is as helpful in understanding a concept as an example. Now, with regard to cyclic groups, U of 8 serves this purpose. It means that is U of 8 is not cyclic. So let's give a let's write it non-example, and let's say that U of 8 is not cyclic group, not a cyclic group. How can we ever verify this? So note that U of 8 have elements which are 1, 3, 5, 7. But in this way, 1 only generates one element. 3 only generates the elements 3 and 1. 5 only generates the elements 5 and 1. Similarly, 7 only generates the elements 7 and 1. So U of 8 is not generated by any of an element for any a n U of 8. Now, with these examples under our belt, we are now ready to tackle cyclic groups in an abstract way and state their key properties. So, the first key property is going to be that theorem 4.1. Okay. Now we are going to present a theorem which says that criterion for a power I equals to a power j, which means that the statement is let G be a group and let A belongs to G if A has infinite order, then order of two elements then A power I is A power j if and only if. I can write if and only if like this, or mm, let's write if and only if, and I'm going in future I'm going to write these I double F. I is j. It is only possible that A power I is equals to A power j if A has infinite order when I and j are equal. So, and if A has finite order, say n, then A is the generator of is generating set. A can generate A square to A power n minus 1, and A power I is equal to A power j if and only if n divides I minus j. So the statement is quite simple, but what it is giving us? It is giving us that when your group is infinite, then it does have infinite elements. But when your group is finite, let's suppose when your group is finite, it can have an element which can generate the entire group, or it may not. But if it has finite an element which has a finite order, then it will generate a subgroup at least of that group. Okay. Now the proof. I'm gonna write the proof over here. So Proof is quite long, but so bear with me. We would try to make it smaller. If A has infinite order, if A has infinite order, there is no non-zero n such that a power n is the identity, right? Since a power I is a power j, implies a power I minus j is e. We must have I minus j is equals to 0. And the first statement of the theorem is proved. And the first statement of the theorem is proved, right? Now, assume that order of A is some n, okay? We will prove that it will generate a set. We will prove that A will generate the set E A square up to a power n minus 1. Certainly, certainly, the elements E A to a power n minus 1 are in the set generated by A. Yes. Now we suppose that now we suppose that a power k is an arbitrary member of the set, is an arbitrary member of set generated by A. By the division algorithm, there exists an integer by division algorithm. There exist integers q and r such that a can be written as qn plus r with the condition that r is between 0 and n. Okay. Then then we can write a power k is a power qn plus r, and we can also write it as qn into a power r and a power n power q a power r and this is a power n is just e, and we get e power q, which is just e, and then we get a power r, and we get power r. So a power k is a power r. So so that a power k indeed belongs to the set generated by a. Okay, this proves that uh, let's write this explicitly. A power k belongs to this set a square and a power n minus 1, and this proves that a generates the set, because we can, with this way we can always get all these elements. Next we assume that next we assume that a power I is a power j, implies that a power I minus j is equals to identity. Again, by the division algorithm, again by the we would shortcut division algorithm. I should write here E A. Okay, let me make the space first. Right, now I can write D A. Okay, again by the division algorithm, there are integers Q and R, such that we can write I minus J is equals to Qn plus R, with the condition that R is between 0 and n. Then a power I minus j is a power Qn plus R, and therefore E is equals to a power Qn plus R, and the same pattern, a power n, power q, a power R, e power q, a power R, and that is e, a power R, and a power R. Since n is the least positive integer, since n is the least positive integer, such that a power n is the identity, we must have R is 0, so that n divides I minus j. Now conversely, if we say I minus j is nq, then a power I minus j is a power nq, which is e power q, which is e. So that we have a power I is equals to a power j, and that's it. So the first claim was, if A has infinite order, then if then it is only possible when a power I is equals to a power j when they are same. And we showed that if A is infinite order, then there is a non-zero n such that a power n is the identity. And since they two are equal, then their subtraction, a power I minus 1, I minus j, should be e. And for this, we must have I minus j is equals to 0. And the first statement of the theorem is proved. Okay. Now, then we had the thing that which says if A has infinite order and say n, which is n, then it can generate a set of something like of this form, and a power I is equals to a power j if and only if n divides I minus j. And we did prove that by saying that A can generate something like this when A have order n, and by division algorithm, following the division algorithm, we show that when we take some k, A power k, it is nothing but inside, and it is an element inside the set. This proved that A is generating this set, and then we had to show that A power I is equals to A power j, then n should divide I minus j, and then we did that, and that's the proof, right? I would present the corollaries, but that would be that I will done in the. So it is good to present one or two corollaries in this lecture. So let's say we have corollary. Say one, which is that order of A is same as order of the state generated by A. And the statement for this one is for any group element A, order of A is equals to the order of state generated by A. And this is simple as that. One special case of 4.1 occurs so that it deserves singling out. Moreover, corollary 2 is going to be says that A power k is E implies that A divides order of A divides A. And this is interesting one. So you are saying actually, this is true, you are saying actually that let G be a group and let A be an element of order n in G. If A power k is E, then n divides k. Say A is of order 2, and then A power 4 is E. Say suppose if A power 4 or A power 6, A power 8 is E, then indeed n is dividing k. There's something like that. Now, proof. Remember, for example, is not a proof. Okay, so we need to give a proof. Since we have A power k is equals to E, which is A power 0, we know by theorem 4.1 that n divides k minus 0. We know by theorem 4.1 that n divides k minus 0. Okay, because A power k is equal to A power 0. And that's the condition, right? Right. And the last corollary would be says that what is the relationship between relationship between order of AB and order of A multiply order of B. And this says that if A and B belong to a finite group, belong to a finite group, and AB is equals to BA, then order of AB divides order of A into order of B. And this is a very strong statement, but it's a consequence of theorem 4.1. So let's prove it. So let order of A is some M and order of B is some N. And then we write that order of A power AB power N M is A power M whole power N, B power N whole power M, and this is E power N E power M, which is E. So, by corollary 2 of theorem 4.1, we have have that what was the corollary 2? Corollary 2 was if you write A power k is E, then order of A should divide k. Similarly, if you say that order of A and is M, order of B is M, N, and then AB power M, M is E, then it means that order of A and order of B should divide Order of AB should divide the product of order of A and order B, which is NM. We have that order of AB divides MN, and that's the proof. And one is just a consequence. Okay. Okay. Perfect. And here we will end our lecture. In the next lecture, we will talk about some other property of the cyclic groups. Thank you so much.